A buffered solution, or a buffer, is a mixture of a weak, either a weak acid or a weak base, and a common ion salt. Such solutions resist changes in their pH. In other words, if we add some acid to a buffered solution, the pH will drop a little. If we add some more acid, it'll drop a little more. If we add a little more acid, it'll drop a little more. If we add some base in, the pH will increase just a little, not much. In other words, buffered solutions tend to maintain a relatively constant pH, even if we try to change that pH by adding an acid or a base. Here are some examples of buffered solutions: acetic acid and sodium acetate. We have acetic acid, which is a weak, and we have sodium acetate, which is a salt that has an ion in common with the weak. Here's another example: bromous acid and calcium bromite. Bromous acid is weak, and calcium bromite is a salt that has an ion in common with the weak. Ammonia and ammonium chloride. Ammonia is a weak base. Ammonium chloride is a common ion salt. And one more example: hydrofluoric acid, which is a weak acid, and potassium fluoride, which is a salt that has the fluoride ion in common. So that's what a buffer is. Obviously, we've talked about the common ion effect in a few previous lessons. The common ion effect plays a role in the operation of buffers. How does a buffer work? Let's consider a buffer containing the weak chlorous acid and the salt lithium chlorite. First of all, we have what we need for a buffer. We have a weak, in this case chlorous acid, HClO2, and we have a salt, lithium chlorite, that has the chlorite ion in common with the acid. So, we have a buffer. Because of the weak, we've got plenty of chlorous acid. It is the weak, after all. In other words, we've got plenty of stuff that could, if needed, donate a proton. In this case, because of the salt, we've got plenty of chlorite ion, and chlorite ion, hopefully you are convinced that the chlorite ion would be quite happy to accept a proton. Because of the weak and because of the salt combined, we've got plenty of some species in the solution that is available to either accept a proton if needed or donate a proton if needed. Thus, if some strong acid is added to this buffer, the chlorite ion will accept protons. In other words, we're going to add some acid in. The chloride ion is going to say, oh, I'll take some of those protons. I'll take those protons. I'll take those protons. I'll take them. The pH won't change much. If some strong base is added, the chlorous acid will donate protons. In other words, that species will provide protons. In either case, the pH of the buffer remains relatively stable. The amount of added strong acid or added strong base that a buffer can handle before the pH begins to change appreciably is called the buffer capacity. Buffer capacity increases with greater moles of both weak and salt. If you remember, the relation molarity is moles per liter. For greater number of moles, wouldn't that mean greater concentration and greater solution volume? So, the more moles of weak and the more moles of salt we have in the mix, the greater the buffer capacity. Ironically, while buffer capacity depends on the absolute amounts of both weak and salt, the pH of a buffered system at any given time depends only on the ratio of the two. We'll talk more about this in a subsequent lesson, but the pH of a buffered system does not depend on the absolute amounts of weak and salt, only on their ratio. The buffer capacity depends on the absolute amounts of weakened salt, the number of moles. Let's end this by looking at the graph of a buffered system, which, as you can see, starts out basic with a pH of 12, and down in the bottom we're adding acid in. You can see that as we add milliliters of acid, the pH is dropping. It's dropping, it's dropping, but at first it doesn't drop by that much. We have to add quite a bit of acid before all of a sudden the pH falls off the table, and that's how we know that we've exceeded the buffer capacity.